Okay, good morning. Can you hear me in the back? All right, loud enough? All right, well, welcome back from a long weekend. Okay, this sounds loud. I'm going to turn it down a bit. Still can hear me in the back? Can you hear me in the back as you're walking in? Yep? All right, good. Okay, welcome back. Hopefully all of you had a pleasant, long weekend. I think we're just going to hit the ground running today. There's a lot to cover. So let's just go into it. Of course, we're keeping our drumbeat here of labs due every Friday. For the next few weeks, that's what's going to happen. Lab 2 is already out. Some of you have already finished it, which is great, but it's due on Friday. Okay. Lab 3 we'll make available as well, probably on Friday, just before this one is due. Okay, so any questions about anything to start with? Yeah, question.
So, how much can we modify the lab code? Do we have to follow the exact steps they did?
No, you don't. I mean, at the end of the day, we're just checking to see if you get the right results. And if your code doesn't work, we'll visually inspect it, but we don't expect that you follow it exactly. Okay. So you're free to deviate if you like. Good. Any other questions? Great. Okay. What we're going to talk about today is continuing on with this idea of matrix multiply, which we kind of unpacked for the first time last time we were all together on Thursday. So we'll kind of pick it up right where we left off, kind of refresh our minds about the computational pattern, about the issues we faced, and we'll pick it up from there. Okay. By the end of today's lecture, what we're going to do is address the issue that we ran into last time, which is we wrote this really simple matrix multiply kernel, thinking that, well, we're going to get really high performance on it, only to realize with some simple calculation that we're limited by memory bandwidth. So today we're going to fix that by adding a few elements to the matrix multiply kernel. Okay, and by the end of today's lecture, we'll write some code, you'll see the code, and voila, we'll be fixed the issue. And essentially what we're going to talk about is what you'll do for lab 3. Okay. So with that in mind, let's kind of open it up kind of get our brains activated. This has nothing to do with matrix multiply, but it's kind of a general question about parallelism. Very simple kernel. There's one parameter, which is a pointer to some memory location x, and each thread is going to increment x. Okay, so if we have 128 threads executing this code, what do we expect in memory location x? I guess I should have said if x started out with the value 0. Yeah, somebody is bold enough to raise their hand first. Go ahead.
Because they're all doing it at the same time, they would all read the same 0, increment that 0 to 1, so it will be 1.
Very good, but you're wrong. But I like the way you're thinking about it, which is, okay, I've got a bunch of threads. They all start off at the same point. They all execute the same code. They all read the same value initially, which is 0. They increment it, and they write it back. So I'm expecting the value 1. the logic is good, except you've made an incorrect assumption. And I'm going to ask you to help.
Yeah, so it's non-deterministic behavior. It could be any value from 1 to 128 because it's a data race.
Okay, so he used the word data race. But he kind of gave a very correct answer, which is the value could be anywhere between 1 and 128. We don't know because of some reason. He used the word data race, but what does that mean? Let's see if somebody can help analyze this.
Data race would be when there's contention between threads where each thread is trying to write to the same like memory location, for example, in this case, and whichever thread does it first or last is, I guess last in this case, is what the actual value of that memory location will be.
Good, okay, so now we're picking it apart. Let me just jump in, okay? So what I like to do when analyzing problems like this is to break it down into its basic elements. Okay, so if we were to take that code and compile it down into instructions that the hardware actually executes, what does that x++ turn into? By the way, if you don't know C or uncomfortable with that notation, it's just x equals x plus 1. So if I take a look at that x equal x plus 1, what does it turn into? Yes?
It turns into like fetching the value of x, doing some math in some registers, and then taking that value and storing it back.
Thank you, exactly. So he said, we load the value of x. Let me just write that down. So this one instruction in C is going to turn into, well, let's get the value of x, which is where? In global memory. It's far away. So I've got to get it. And there's an instruction that lets me do that, which we'll generically call it a load. And where do I put that value of x? Well, I'm going to put it in a register so I can manipulate that value somehow. So let's say I put it in register 1. Whatever the syntax is doesn't matter. The idea is taking the value of x and bringing it into some close by storage, which we'll call a register. Once that value is there, what we'll do is just add 1 to it. That said, what's the last thing I'm going to do? I'll put it back, right? Because I've added 1 to it. Well, let's store it back. So that's the companion instruction to a load, store, and I will take the value of R1 and put it back in X. Again, that's just some syntax pseudocode I made up. But hopefully the idea is clear. So when I'm executing, when a thread is executing this code, it's essentially executing those 3 instructions. Okay, so those 3 instructions execute for every single one of the 128 threads. So now what we are asking is really, well, how are those instructions in time interleaved? Do we know? Actually, we know a few things, but what do we know? Yeah.
Well, so we know that it's going to schedule, those 128 threads into, 6 warp, divided by 32 warps. So.
Give me a hint, 4.
4, yeah.
Okay, 4. 4 warps.
Into 4 warps. So at that point, even with all the, I'm going to say, data race ambiguity, we're guaranteed to get 4 because, at the end of the day, it's all. The first set of 32 starts with 0, and then the last one's always going to write 1. I mean, this is assuming, again, that they all read simultaneously, but if in that ideal world, then the first stage would get a result of 1 stored, then the second warp would run, resulting 2, then 3, then 4.
Great. So what he's done is he said, okay, 128 threads. Well, what do I know? I know that they execute in warps. And those warps execute all at the same time, 1 instruction. But between them, I don't know what order they execute. They could execute serially, or they could all execute in parallel. It's undefined. So let's take the case where two threads are executing and it's undefined as to what their order is. Okay, we'll just make it very, very simple to begin with. Two threads, I don't know which order they execute in. And now, kind of in your mind, you can start to do all the interleavings between those two threads. Thread 0, thread 1. Maybe thread 0 executes the load first. Maybe thread 0 executes the add first. So now, in register 1, it has a 1. And now maybe thread 1 races ahead. There's that word, race. Load, add, store. So it is stored a 1 in memory location X. Thread 0 hasn't executed the store yet, but now it does. It stores a 1. So here, those two threads, because of the way that we've interleaved it, have stored a 1. Can we ever store a 0 as a result of those two threads? No, because one of them will succeed in storing at the last point, right? And whatever it stores, which will always be greater than 0. Right? So that makes sense. What's the interleaving for those two threads that gives us a 2? Yeah.
The load for one happens after the store for another.
Very nice. So the store of one completes before the load of the other. When that situation is met, we'll get a 2. Okay, now we extend it to 128 threads. Right? That's the idea. So clearly, if that's the code we wanted, we didn't really want all that unknown associated with it, right? Because, I mean, it's not very good to have a piece of code like that generate an unknown value or non-deterministic value. So we would never write code like that, first of all. Or deliberately. I mean, maybe there's some reason, but so how do we fix that? Question, yeah.
If you have 4 warps, and so every thread in a warp is, they're all parallel, right? So how come it's not between 0 and 4?
Good. Okay, so now let's introduce the idea of warps, because I kind of neglected the warp first. Okay. If in a warp, I mean, there's a little caveat here. I'm going to put an asterisk, because Cuda is going to do some optimization internally that's going to mess up the warp. But based on what we know about warps, 32 threads executing the same thing at the same time. Okay? So if that's the simple model, then what is the value that we could expect? What are the values we could expect in X?
1, 2, 3, 4.
1, 2, 3, 4. Exactly, because all the warps will load at the same time. All the threads within the warp will load at the same time. The same value. And they'll store at the same time. What does store at the same time mean? It doesn't really matter because they're all storing the same value, but there's no implied ordering, by the way, on that store. Anyway, the point here is we've got this interleaving that's non-deterministic. So how do we fix that? What is the thing that essentially broke between what we wanted and what we got? We made an assumption. What was that assumption? Let's see if we can think a bit abstractly here. Somebody said it, but we'll give you another shot. Yeah.
I think we have to make sure that they load sequentially and add in parallel and then store sequentially.
That's a complex answer. It may not be right, but I like the way you think. But there's a simpler way to approach it. Yeah.
I think the intention of this piece of code, this code assumes the operation is atomic. So if we want to make the
results correct, we need to make it actually atomic. In
Good. Let me interrupt you and complete your thought, okay? Because you said the right thing, which is when we executed that x++, our intention was that x++ was happening atomically. When the hardware actually executed it, it divided it into 3 instructions. This is not some hypothetical piece of hardware executing hypothetically 3 instructions. It's universally that's how hardware will execute. Okay, with 3 primitive instructions. So really what we want to do is we don't want those instructions to be indivisible in time. That is, what I load is what I load when I do that store. That some other store hasn't come in and written that value. Okay, so we want these things to execute. We use the word atomically. So these 3 instructions execute as a unit. Or atomically. So we'll introduce something that does that. In fact, I just want to kind of put it in our minds. Let's say we had a way to do that. Atomic add x, 1. Go to memory location x, add 1 to it, and make sure nothing else comes in between. So if we replace the x++ with that, boom, problem solved. 128. Okay, makes sense? Keep this in your mind. It's going to pop up before we get through with today's lecture. Okay, any questions about this? Yes?
How would the performance of an atomic add compare to the serial add?
Yeah, that's a very good question. It's awful. Okay. We just don't want to sprinkle these in willy-nilly, because essentially, to implement this in the hardware, we have to prevent all other threads from modifying x while one thread is modifying x. So it imposes some kind of serialization that's going to make things kind of, for the moment, become sequential, right? And that's going to have a performance penalty associated with it. Yes?
Let's say we want like true parallel behavior there and we just want x to be 1. Would just making sure they all load at the same time fix all problems of this nature?
Yes, but how do you ensure that all your threads load at the same time?
Or by prevent, I don't know, like do parallel load. Is it possible?
If it were possible, sure, we could do that. Yeah, if we were okay with a 1 there. Okay. Let's move on, because we're going to see this pop up in a real context. I've done a lot of Cuda work, like with real commercial code. And this, unfortunately, becomes a performance limiter. You have to use it. And it causes an undue amount of serialization. We'll get to it. Okay, let's move on. There is a question. Let's take one question before we talk about matrix multiply. Yes?
Since in parallel programs we have to use atomic somewhere usually, and GPUs are very optimized for parallel but not serial work. Can we like do simultaneously do parallel on GPU and serial on CPU?
Yeah. So his point is, well, I'm gonna embellish your question. His question is, okay, this kind of stuff is awful on a CPU, you just said. Is there a way for us to do this maybe on the CPU or anything like it? The answer is yes, and we're going to see examples of that before the end of the semester. Okay. Let's move on, because the topic is not really this. The topic is this: matrix multiply. All right, so we wrote some code last time. This is not GPU code. This is the CPU version of matrix multiply. And again, just to refresh our memories, what we have is matrix M, matrix N, and the result, P equals M times N. And in the simple version that we're doing in class on the projector is that we're assuming they all have dimension width. So they're square matrices with dimension width. And what we have is essentially width times width as the result matrix P. And what we want to calculate is for each element of P, the dot product of this row vector and that column vector. That's what a matrix multiply is. So if we wrote it out in C code, there it is. So it's a triply nested loop, width by width by width. And within the inner part of the loop, what we're doing is essentially calculating the dot product. Get an element of M, get an element of N, multiply them together, and store them in the accumulating sum that is ultimately the result. Okay, so the algorithmic complexity of this is width cubed, right? Because you've got 3 loops, the dimension of each of those loops is width. So it's a very compute-heavy problem, matrix multiply. And if we're looking at real-world systems, these matrices can be tens of thousands, hundreds of thousands of elements. Right? So we're talking about a lot of computation for big systems. So yeah, we want to accelerate this using GPUs. And to some degree, it's an ideal candidate. Okay. Any questions to begin with about the simple CPU version of matrix multiply? It's a bit of a refresher, right? So what we decided to do was to take this and say, okay, we're going to map it into a Cuda kernel where each Cuda thread is going to calculate one output element. So we've got n squared, or width squared output elements, and one thread, one output element. It's a nice mapping, by the way. So now if we're going to do that, then we have to figure out how we're going to create the blocks. And to maintain the 2D structure of the computation, we're going to have 2D blocks. In this case, the block width is 4. So 4 by 4 blocks, 16 threads per block, arranged in what we call tiles, blocks tiles, of width 4. Okay, so in this case, we'll have 4 blocks, each block having 16 threads. That's just an example here. So if we wrote out the kernel invocation code, which, by the way, this is independent of block width. It's a parameter here. We're going to dimension the dimension the grid with block width by block width. Dimension the grid by taking the width of the result matrix, dividing it by block width in both dimensions, x and y. That's the number of blocks up and the number of blocks over. And then within each block, we have block width by block width threads. And we can launch our kernel from there. Okay. And the code we came up with to do this was rather simple. What we do is, first, we calculate the row and the column of the output, which is just kind of taking block dimensions in the y dimension and multiplying it by the block index in the y, adding it to the thread index. And likewise for column, doing the same thing. Okay. we calculate row and column, which is the row and column coordinates of the output, and then doing the dot product here. Right? So the outer two iterations, the outer two loops of the C version are gone. And we just calculate from the outer two iterations the row and the column indices, and then we do the dot product. Right? Make sense? Let me carry on a bit and we can come back and take some questions. Now, within the dot product, this is where all the work happens. Okay. What we have is, we have some computation to go from the row to figure out which vector or which element of M we want to read. And likewise, a little bit of arithmetic to calculate which element of N we want. We do the floating point add, multiply, floating point add, and we store the result in p-value. Okay. Now, I'm just going to make a very crude simplification at the moment. And I'm going to say that, well, the amount of computation I need to calculate this and calculate this is actually small. Okay. I mean, it looks like there's stuff going on here, but it's integer arithmetic. And if I kind of mess around with the arithmetic in this loop, it's actually just an addition. So I'm not going to worry about how much compute there is in here. But in terms of floating point operations, I've got one multiply, one add, a load, and a load. Right? So I'm loading two values, multiplying them together, and then storing the result. I'm sorry, and adding to the accumulated sum. So two loads, a multiply and an add. Again, bear with me, I'm taking all the integer address calculation, and I'm saying that it doesn't count, because it really doesn't count in this case. Question?
Can you throw the matrices in the cache?
We will, except we won't call it a cache. We're going to call it a shared memory. Okay, so the point of all this is, if I calculate how much memory bandwidth I need, and we did this last time, so I won't belabor it too much, what we're going to find out is this code is memory bandwidth limited. I can't execute enough instructions because I'm just pulling data from global memory into the SMs. I'm limited by that. Go through a simple computation here to to realize that. Okay, so somehow I have to change the equation. Really, what I have in this loop, in this kernel, is one floating point operation for one load. And on a GPU, I might have 10 times as much floating point bandwidth as I have load bandwidth, memory bandwidth. So I've got to change this somehow. So that's what we're going to do. Any questions before we move on? This is just a recap, of what we discussed last time. Question?
Two quick questions. One, just this flop, floating point operation, same as FPI.
Yes. Flop, sorry, I'm maybe a little casual in my terminology here. Flop means floating point operations per second. Okay, that's what flop means. So when we say flop, it's really counting multiplies and adds. Floating point multiplies and adds, in this case. And your second question?
So second question was, we talked about like how the grid is up to 3 dimensions, right? Is the purpose of that more about like where the last slide we're calculating the row and column to simplify
Yes,
that? Or
absolutely.
Okay. Is
Yeah.
there any like actual performance side?
No,
benefit?
no. It's just convenience for the way we end up doing these address calculations. Absolutely. Yeah, question. Why aren't we not considering, sorry? Okay, I'm sorry. Let me come back here. So I think your question is, these here seem to be within the inner loop, right? Is that what you're saying? Why are we not counting those? Well, first of all, they're integer operations. Okay. It's just integer k times integer width plus integer column. Okay, same thing here. So they're not floating point, first of all. But the other thing is, because they're not floating point, they happen almost for free. Okay. But the other thing is, if I optimize this loop, it's actually just one add that's here. Because I pull out all the constants when I optimize the loop. So it's one add and another add. And those adds kind of happen for free for us. Okay. So let's not dwell on this. Let's move on. Okay. Let's let it be known that this, if you were to write this code, your performance on this kernel would be pretty lousy because we're limited by the memory bandwidth. That's the point. Okay. All right. So how do we avoid this? How do we get around this? There's a lot of text on this slide. There's only one point I want to make, or 2 points. First, if I take a look at the elements of M and N, right? So M is a matrix, N is a matrix, it's got a bunch of elements. How often is each element used? Or width times, right? Because we kind of evaluate when we do these dot products, right? I'll show you. Coming back to this, right? Here is a row of M. That same row of M is going to be used for every item that's along this dimension in the result matrix P. And only there. I'm not using it anywhere else. So I'm reusing each element of M width times. Okay? Well, that's great because I can do something with that. Let me come back to this. So if I've got that kind of reuse, I don't want to go back and refetch it from global memory because clearly it's hurting my performance. So what we are going to do is we're going to use something called shared memory on the SM to alleviate this issue. Okay. Now, if you're familiar with CPU architecture, you know this idea of caches. And as a programmer, thankfully, we don't have to worry about the cache. It's an implicit structure that with some very simple rules, the hardware figures out or predicts, really, what I'm likely to reuse and puts it in the cache. And it's great because we don't have to think about it, and we essentially get the benefit of that cache. Well, in the GPU world, these caches are software managed, meaning we have to write the code to put the data in the cache when we want to use it. In fact, it's not a cache at that point. It's a software managed memory. That is what the SM shared memory is all about. Okay, let's see how it works. Question, or can you wait? All right. Okay, so that's where we are. We've got this little memory, and what we want to do is essentially in the previous version of our algorithm, we had all these threads pulling all this data from global memory, and it created a situation where the global memory became a bottleneck. Now what we want to do conceptually is introduce a relatively tiny, in fact it's pretty crazy about how tiny this thing can be. So relatively tiny shared memory where the threads don't have to get their data from global memory directly, but most of the time can get their data from this shared memory. And the shared memory has ample bandwidth relative to the global memory. Okay. That's what we want to do conceptually. Now, if we come back to the Cuda SM architecture, what we have is this streaming multiprocessor that has a bunch of execution hardware. And attached to that execution hardware is a bunch of memories. And I've shown here what those memories are in terms of sizes based on the Ampere architecture, which is the latest NVIDIA architecture. So depending on the GPU you're using, the sizes are going to be different. But the idea is the same. There's a register file where all your local variables are essentially allocated in the register file. We've got what is a L1 cache, which we're going to ignore, but it's very tiny. L1 cache, we'll ignore it for now. And we have this thing here, a shared memory, which is what we're going to talk about today, which is primarily how CUDA programmers bring and store data close to the SM. And you can see in terms of their access latency, how all these things fare up. What I didn't put on here is from things like shared memory, we can actually do many, many loads in parallel. Each thread can load from shared memory in one clock cycle. So we've got lots of local bandwidth here. We don't have to be limited by it, like we are with global memory. Okay, so lots of bandwidth and low latency, but it's tiny. And we have to manage it ourselves, right? Those are the downsides. Question?
So this shared memory looks pretty small, and I'm assuming a certain number of threads would share some shared memory. Is there a clean way to map how we would divide up a large matrix into shared memory for the relevant threads?
So here's the thing. So his question is there a clean way to map the work we want to do into a shared memory? And the answer is it becomes part of our algorithm design. Okay. What I said was in the GPU world where we just have these caches, we don't care primarily. They just work. I do a load, maybe that load hits in the cache or maybe I have to go to memory. Our code is oblivious. In the GPU world, our algorithm now has to be kind of crafted for the fact that we have a shared memory. And it changes things substantially. Okay, and we're going to see that in a moment. Question?
Is there some sort of, so like depending on like how we want to chunk it, or like, is there some sort of, I don't know, maybe keyword or directive or something that we can use inside of our code to like pseudo query the compute capability to figure out?
Yeah, there is. I'll tell you at the end of the lecture. Yes, I'll tell you at the end of the lecture. Okay, one more question and we'll move on. Yes?
If you're trying to parallelize something in which each independent operation only needs one memory location, is it worth it to take that global memory and put in shared memory?
Okay, so his question is, if there is no sharing, right? If there is no sharing between the threads, does it make sense to put data in shared memory? That's a very good question. That's like an exam quality question. So let me repeat. If there is no sharing between threads, does it make sense for us to put data in shared memory? Was that your question? Okay, good. And clearly, if I make a big deal out of it, there's something subtle here that you need to think through. Yeah, you want to answer your own question?
Yeah, I was going to ask, does it depend on the time it takes for global memory to write to shared memory, and if it's different than just a normal global memory fetch?
You're kind of converging. There's a very simple thing I want someone to say. Yes? Perfect. So her response is, well, what if that one thread that's using that location repeatedly accesses that location? Well, hopefully the compiler will have put it in the register file, but if it hasn't, and we want to guarantee that we can reuse that value, hey, maybe we'll just put it in shared memory, right? Is that what you were saying? Right. Make sense? Okay, good. Let's get to the heart of the matter now. So, in the world of CPUs, this shared memory, we call it a cache, is implicit. We don't think about it, but we benefit from it. In the world of a GPU, this shared memory is explicit. We have to, in our code, decide when we're using it and how we're using it. So in Cuda, we can declare a memory object to be allocated in shared memory by putting the __ shared qualifier on it. Okay, so what that does is it takes subtile M and puts it in shared memory. It's not in global memory, it's only in shared memory. And furthermore, it's shared by all the threads within the block. Okay, so that's an important thing to remember. That it's not shared by all the threads, but it's shared by all the threads in the same block. So if I declare subtile M to be tile width by tile width, what I have is something that's the same size as my block, or whatever tile width is, that's allocated in shared memory. Okay, likewise with subtile N. That's the first thing. That's the simple thing, right? I want to put something in shared memory. The way I do that is just by putting the __ shared. That's it. Now it's in shared memory. Question?
What happens if we declare a shared array that's too big for shared memory? Will it just go to global memory?
Good question. What happens if we declare a shared object that is bigger than what we can fit on the compute device? You'll get an error. It won't compile. Actually, it'll compile, but it won't run. Yes?
Can the size of the shared memory be determined dynamically?
No. It needs to be, it needs to be known that's a good question. I have to come back to you. I think it has to be known before my code runs, before the kernel is launched. Yeah, I think that's right. Question? Okay, so it's at launch time, kernel launch time. Yeah, I think that's what you're saying. Let's move on, right? These are all good questions. Don't want to lose the bigger picture here. Okay, so here's the gist of it. So we've got this shared memory. And what we're going to do, and by the way, let me pause here. There are many ways to do what I'm about to do. If you're creative, you can come up with your own way. This is kind of the way most matrix multiplies are implemented on Cuda. Okay, because again, we have to use shared memory, and this is like the most straightforward way of doing it. Okay, so coming back to it, right, what we're trying to do is we've got all these threads in this output block right here. And it's tile width by tile width in terms of the dimensions of this block. Okay. So what we're going to do, and by the way, the realization is, hey, I've got this vector here that I'm doing a dot product with the column vector there. And across all of these, I'm reusing the elements of this. Oh, and by the way, across all of this, I'm reusing all of the elements of the column vector. Okay, so rather than picking which one I'm going to stick in the cache, the shared memory, why don't we put pieces of both of them? Okay, so we've got this as our output. Now, conceptually, in calculating all these output elements, I'm reading all of these elements of M and all of those elements of N, right? So it's like a big bundle of data across the columns and a similar bundle of data across the rows that correspond to the output elements. Here's the trick. What we're going to do is we're going to say, well, we're not going to calculate the products, the dot products, all at once. We're going to calculate the partial dot products. Okay, meaning let's grab this blue. Let's grab the blue. That's a part of the input and a part of the input. Let's put those in shared memory. Okay, once those are in shared memory, all the threads calculate this much of their dot product. Right? In order to calculate this much of the dot product, I need that much of those column vectors. Okay, once that's done, we'll calculate the next set of partial products, which needs that much of matrix N, and so on and so forth, until we have gone through and done all tiles across the input spans. Okay, so we're taking that dot product that was in the innermost loop, and we're doing it a chunk at a time, right? And when we do the chunk, the first thing we'll do is we'll take the input M and N and we'll put them into shared memory. Sounds complex, right? There's a lot of pieces here, and indeed. But what you'll be surprised to see is that once we write all the code, it'll fit right on the screen. It is not, at the end of the day, a lot of code. Question? It's a good question. I like the question, but we're going to assume something very simple. We're going to do it this, then this, then this, then this. So we're going to execute them in serial. Okay, just to keep it simple. But clearly you're one step ahead, right? You can see that, yeah, maybe I can execute them in parallel. Okay, so we can keep it simple, do the blue ones, then the orange ones, and then so on and so on and so on, one at a time. Okay. In fact, the thread mapping hasn't changed, meaning each thread is calculating one element of the output. Okay, let's start to put all of it together, right? So for the next, I don't know, let's say 10 minutes. We're going to build up the code one step at a time. Okay, maybe 15 minutes it'll take us. All right? So let's do it conceptually first. So what I have, but let me make it clear. So we created underscore shared subtile n. We created subtile m and subtile n. Let me just use, for example, subtile n. If I want to load something into the shared memory, how do you think I do that? Like, that's a shared memory variable. I want to put something in it. How do I do it? Go back to basic principles. Yeah. Regular assignment. Works just fine. So what I could do is subtile n x y equals n whatever I want to put in there. So n is a variable that's in global memory. It's a memory object in global memory. It's the input. If I pull an element of n and put it in subtile n, well, now that thing is in shared memory. That's it. That's all we need to do. That's how we're going to manipulate shared memory. Okay, so let's remember that. Now, okay, so we've got a little toy example here. We've got 16 elements of M, 16 elements of N, 16 elements of P, 4 by 4. And in this case, block size tile width, which I'm going to use interchangeably, is 2 by 2. So four threads per block. So let's draw our attention to block 0, 0, 0, which is calculating these 4 elements. Okay. So what is block 0 doing initially? Well, block 0 needs to take this chunk of input n, m, and load it into shared memory. And the same corresponding thing from n and load it into shared memory. Right? That's the first thing we need to do. Okay, once those things are in shared memory, we can do some of the partial computation. So they're in shared memory. Now I'm going to calculate, in this case here, I'm just going to draw our attention to this element here, this thread that's calculating P00. What it will do in this step is take N0, 0, M0, 0, and multiply those together. And these are in shared memory at this point. Okay, so we're just calculating the first element of the dot product. And that's what all the threads here are doing. Okay, next step is, well, we are here, let's take the next element, M01, and multiply it by N10. So we've calculated another element in the dot product. So at this point, we are done with that part of shared memory. What we need to do next in order to calculate this is load the next tile of the input. So we finished up this tile, and now we're getting the next tile. Okay, so we load those, we calculate the next part of the partial product, and then the next part of the partial product, and then we're done. Actually, we've completed the work there. Okay, so let me say it one more time in a slightly different way. So going back, what we are doing is loading a tile from M, and loading a tile from M, computing the partial product, loading the next tile, computing the partial product, next tile, partial product. Okay, and you may be wondering, am I saving anything by doing this? Like, I'm loading all these things into shared memory. Sounds like I have to do those loads anyways. But does that result in a net benefit? And we'll see. It's pretty substantial. Okay, so conceptually, let's take a quick pause here. Any questions about the algorithm itself? Yes?
So just to clarify, a block is calculating a tile of the output, and that results in loading multiple tiles from inputs M and N.
Yes. Yeah. What we're doing is, let's use the word chunking or tiling. The tiling is what we will use in general. But we're taking the input and we're loading one tile at a time. And why are we doing that? Because we're going to take one tile, put it in shared memory, reuse quite a bit. Once we're done, get the next tile. Okay. And that's going to result in a substantial improvement in performance. Yes?
So, some of the tiles you'll reuse them. Or do you optimize that in some way and say, like,
We won't, not in matrix multiply. Right? In matrix multiply, the only output, actually you're right. No, you're right. Sorry. So let me make sure I understand what you're saying. So what he's saying is, okay, take a look at this blue block here. Okay. Yes, it's true that all the elements of this are going to use the blue block. But it's also true that all these elements are going to use the blue block, right? I'm clearly not utilizing that fact here, but I could. Like I said, there are many, many variations on this, right? You could come in with a different kind of approach, and it'd still be right, or it may even be better. Okay, that's good point. Yeah, question. Yeah, we're going to keep it simple and say that if this is the block size, we're going to keep tile width to be the same. They don't have to. You can get creative. Yes?
within each tile, is the multiply algorithm the same as?
Yes. Yeah, it's just that what we've done is we've taken the original algorithm, which is just, iterate through all the elements and calculate the dot product. And we're kind of doing this. Iterate through all the elements in a tile. Calculate the dot product. Pause. Get new shared memory. Calculate all the elements of the partial dot product. Pause. Get new shared memory. And so on and so forth. Yeah, that's essentially what we've done here. Yes?
So we calculate these partial products, but at the end we're going to have to, reconstitute them into the actual final, non-partial, the complete product. So, where would we store these?
It turns out it's easy, right? Because what we're doing is it's a single variable per thread. It's a single value per thread, right? You'll see. We'll get there. One question before we move on. Yes?
Where do we actually, syntactically create the shared memory? Because if we do it inside the code that's per thread, would it, replicate that?
A good question. So syntactically, how does all this fit together? Let's get there, okay? These are all good questions. Okay, now, what I would expect is, for some of you, you're like, yeah, this makes sense. I get it. And conceptually, you're going to see the details and hopefully weave it all together. Maybe others are like, man, I'm totally lost. I followed up until the point where this slide came up, and then I'm not getting it. Don't worry, because what we'll do is we'll still show you the details. And if you're conceptually there, you'll be able to piece it together later tonight or tomorrow. And certainly by the time you do Lab 3, which is a week from Friday. Okay. By the way, in Lab 3, what you'll do is this, except we're going to not have it be a square matrix, so the dimensions can be different. Okay. Okay, any other, well, let's move on. Okay. So we kind of went through this, and what I want to do now is start to develop the code. Okay, so let's start off with something super easy and super concrete. The blue tile, right? In order for us to calculate the output here, we need the blue tiles to start with. Okay, so what we know is, okay, I have this output element that any thread is computing, and I know what its tx is, I know what its ty is, thread index y and thread index x, because those are given to me by those indices. Okay, so I use txy and txx to start to load this tile from shared memory. Into shared memory. Okay, so, and it's quite easy, okay, because what I know is I want M. By the way, I think I missed one crucial element here. How do we load these, the blue elements? How do we load them? I said it's a simple assignment, right? In fact, that assignment is right there. But who does it? We have a bunch of threads. We have, tile width by tile width threads. Who's going to do it? Somebody has to load them. Us. Let's pick a thread number. We could make it easy and we could say, okay, if your thread index X and thread index Y is 0, load all those things in, right? That conceptually seems simple. But why might not that be the best way to do it? Yeah.
We're doing it on serial. Couldn't we just have each sort of thread in the output load the corresponding element to the tile?
Beautiful. So if we said thread index 0, okay, you're 0, go load everything. We're forcing a serialization, which may matter, may not matter, but it's still a serialization. So rather than do it that way, why don't we have all these independent threads load that input? In fact, how many threads do we have? Tile width by tile width. And we've got tile width by tile width plus tile width by tile width. So why not have each thread load 2 elements of M and N, or one element of M, one element of N, and put them into the corresponding shared memory locations. Now we're doing it in parallel. Question?
Well, would parallelizing that even have any benefits? The memory bus at the end of the day is, essentially serial. You block for...
It's not doing it one at a time. It's doing it in parallel. There is parallelism at the memory, okay? But conceptually, we want to do it in parallel. Okay, a couple of questions here. Yeah, let's take yours.
But then in this case, do we need some extra synchronization?
Hang on. The answer is yes, but I'll explain. Yes.
Would it make sense to tile N either like the whole thing or the subtile level? Or to transpose it, sorry.
Say your question again.
Yeah, would it make sense to transpose either N or the subtiles of N?
Would it make sense to transpose N or the subtiles of N? And you're talking about something we will talk about next week. Yeah, but the answer is yes. Okay, but let's not worry about it now. we have chosen to do this in parallel, meaning each thread is going to load one element of n and one element of n, m and n. Okay, so there we go. Those are the two assignments. One element of m, one element of n. That said, if we're looking at the blue, I know the row and the column. I know in the grand scheme of things, in the entire matrix P, what is the row and the column of the output? That's code that's easy for us to do. We know how to do that. We did that in the previous version of the kernel. So I know the row and the column, and I know ty and tx. And really what I'm doing is I'm loading for m, I know the row. Of all the rows, I know which row I need to focus on. And I know I want this element, which in this case is the particular tx of the thread in the block. So cool. And I put it into the corresponding tytx of subtile m. I use the same logic to figure out which element of n to load. Okay, so now each thread, in this case, is loading the appropriate element of the blue block, tile 0 in this case, into shared memory. Well, what about the next tile, tile 1? Okay, well, a little more complex because I need to move everything over to the orange block in this case. Okay. Ty and tx are the same. And now I'm just going to generalize the computation, the address calculation there. So I don't want this element. I want this element, which is 1 times tile width, right? So I need to kind of bump over by tile width and add to it tx. So now I'm getting the appropriate element from m, and I do the corresponding thing with n. Okay, so I've kind of modified my code a bit to handle the next iteration. Now, if I consider the general case, Q, which is, I've got a bunch of these tiles, and, I go from 0 to 1 to Q. For the Qth tile, what I'm going to do is I'm just going to multiply everything by Q, the tile width by Q, in order to find the right indices. Okay, so it's not much more complicated, and I'm just kind of doing simple address calculations to figure this out. And there it is. That's it. That's the biggest change we're going to make right there. Okay. Now, we have to deal with the fact that m and n are not statically sized. Right? We Cuda malloc them. If we're going to Cuda malloc memories, we don't know. The C compiler, the NVIDIA compiler, doesn't know the block dimensions or the dimensions of the matrix. So we kind of have to convert all of the two-dimensional indexing into single-dimension indexing. And again, you're very familiar with that as it is, and I've just kind of pushed the arithmetic through. Okay, so it's no longer a two-dimensional m, it's a single-dimensional m and a single-dimensional n. And we're done. Okay. So if you didn't follow, what I did was I just kind of generalized the computation and converted it from two-dimensional indexing into single-dimensional indexing. Okay? Now with that in mind, we can move on to computing the partial product, which is just to take the value in subtile M, multiply it by the value in subtile N, and store it in this partial product, p-value. Okay, so I'm just taking this little piece of the vector and that little piece of the vector, multiplying them together, dot producting them, calculating their partial dot product, and accumulating the result in p-value. Yes, question?
Also putting the p-value in the shared memory?
Oh, well, we haven't allocated where p-value is. Okay, if we put p-value in shared memory, in fact, that's a great question. I'm going to use that on the exam. I like that question. I make a typo, and I accidentally put p-value in shared memory. What happens? Well, let's handle that at the end of the class. Okay, let's put it all together. Here it is, except it's wrong. And we'll talk about why it's wrong in a moment. But conceptually, it's right. It's just missing a few details. So, lines 1 and 2. That is the declaration. I'm declaring subtile M and subtile N to be allocated in shared memory, tile width by tile width. At this point, I don't think that's a surprise, right? That is clearly, you should all be able to follow that. Then I have these shortcut variables, bx, by, tx, ty, so I don't have to keep writing thread index x and so on and so forth. I calculate row and column, which is in the full matrix P, which element is this thread writing? It's row, column. And then float p-value. So lines 5, 6, 7, where are those things allocated? Let's see who's following. So 5, 6, 7, int, float. Where do they end up? Yeah, on the side there. In the register file. The operative thing here is those are thread private variables. Right? They are copies that each thread has that are different for all threads. So thread 6942, right, will have its own row, its own column, its own p-value, which will be different than any other thread. All right. Back to your question. Who asked the question? Somebody asked the question. You did. What happens if I accidentally put, instead of that, I put shared float so now every thread will use the same p-value. In fact, it will be stored in shared memory. And now we're going to run into the same problem we had at the beginning of the class, which is now we're getting updates to p-value by all the threads, and we really can't understand which happens in which order. Okay. Okay, so here's the good version of the code. And what we're going to do is we've got this iterator here, Q, and Q is going to go from 0 to width divided by tile width. What is that? What do you think that is? Well, that's just the number of those tiles we have in each dimension. Right, so if I go back to the previous example, here, I've got 1, 2, 3, 4, ... whatever fits. along that dimension, which will be the same as whatever fits along that dimension. Okay, so cool. So now, in the inner loop, what I'm going to do is use the fact, okay, so I will load the subtiles, right? So all the threads are loading 2 elements of the subtiles, one for M and one for N, from the appropriate spots in M and N, right? We calculated, we determined that in the previous few slides. And then we go through and we do a little bit of the calculation of p-value. And then we iterate. We get the next tile, next tile, next tile. And eventually we're done. And we store p-value in the right place. Okay, makes sense? Any questions on this code? Yes?
Are we assuming that all the threads are at the same point?
Okay, good. So you're now, we're hitting I think you're getting at a point that's really gonna be my point. Ignoring all timing issues for the moment. Any questions about the logic of this code? Yes? Yeah. Let me just interject here, okay, because we just have a few more minutes. So all the threads are loading elements of M and N from global memory. Okay, so at some point, we will have all of M and N, at least that tile of M and N, loaded into shared memory. Because all the threads are doing it at once. And once they're all done, we have a full piece of M and N in shared memory. And we can use those. So each thread will use elements that were loaded by other threads within this inner loop. So they all load, each loading 2 at a time. But once they're loaded, they all use what the other threads loaded. Okay. How do we know that all the threads are done? Right? We can't start this until we know that all of these are done. And we don't have a guarantee of that because we can have many threads in a thread block, more than 32. So there could be some that are not done before some reach this. So we need a way of preventing threads from progressing until all of this is done. Okay? So I'm going to stop here for today with that idea in mind. So why don't we pick it up on Thursday from this point?
Just had a quick question. So when we talk about shared memory, is that also shared across multiple warps, or is that like switched out every time?
Oh, it's shared amongst all the warps.
Shared amongst all the warps. So what's like the, I guess, unit of the group among which it is shared?
Block.
Got it. All right, cool. Thank you.
Yeah.